Welcome back to COS 217 lecture. In the final two lectures of this course, we're finishing out our downward language level tour with a foray into machine language. We do so with three motivations in mind. Now that we've seen assembly language, which we know has a direct correspondence to the instructions run by the processor, that's good, but we're still left a bit in the dark as to how it works. So learning about machine language can connect the dots from assembly language, which is still human readable, at least for us now, to the actual bits that the hardware sees and interprets as instructions. Second, as noted in the last lecture, Assignment 6's A and A+ attacks require that you write some machine language of your own. Not necessarily a lot, and with a fair bit of scaffolding, but you have to know enough about ARM instructions in machine language to make use of that scaffolding to build yourself a miniature version of an assembler. And finally, we get to remove one more lie. Call it a convenient oversimplification if you don't like the word lie, that you've been dealing with since the beginning of your computer science education, and one that we've been percolating down throughout our C and assembly language coverage. That can finally go away as we dive into exactly what the assembler and linker do at the bit level. We'll address the first two of these motivations today. First, we'll talk about machine code at a high level, then we'll see how it comes into play with the A attack, and then finish up with a lot of ARM specifics that you can use as reference in constructing your attacks. We've seen that high-level languages can be extremely portable, and even ones known to be less portable, like C, are still largely portable. At the lower levels, though, this doesn't hold at all. We saw this at the assembly language level, but it is at least as big an issue at the machine code level. One can think of assembly language as just a one-to-one mapping from assembly instructions into machine language instructions. So, while impractical, one could at least imagine mapping many or even most of the assembly instructions onto the machine languages for different architectures. Think of it as a sort of extension of what already happens with the same assembly language being used for different specific processors within the same architecture family. But I struggle to even think about what it would mean to have completely different architectures share the exact same set of bits defining each of the instructions in their respective machine languages. This doesn't make any sense to me. That means that this portability of high-level languages requires someone else to have done the careful translation of the higher-level language into the system-appropriate lower-level language. We've been relying on this assumption throughout the four-stage build process that we've seen virtually this entire course. As a reminder, the four-stage build process, we have initially the preprocessor, which brings in declarations from a header file, fills in macro replacements, and throwback to assignment 1, decomments. Then there's the compiler. It translates from C to assembly language. We've now done this by hand, but obviously there's a lot more to it. That's about all we're going to say for these first two stages. But if you're interested, COS 320 is a departmental that allows you to build a compiler of your own and deal with all of those gory details. In this course, though, we do still have a little bit of material to cover about the assembling and linking process. The assembler translates from assembly language into machine language, based on knowledge of the correct mapping from the assembly language to the machine language for each instruction in the instruction set. And finally, the linker resolves all of the unfulfilled references within the program and brings external code from libraries and pieces together the final executable. It reads a combination of machine language generated by the assembler and certain assembler-produced directives that help the linker do its job. Today we'll talk about translating simple instructions into machine language, and next time we'll talk about how the assembler prepares for the linker and then the role of the linker itself. You may be asking yourself, even arguendo that I buy why we're doing assembly language, why would I care about the bit-level details of machine language? Well, let me flash back to this slide from the last lecture. We covered this idea of jumping elsewhere in the text section last time. Now we can think about the so-called much, much worse alternative. If we can inject executable code into the data of our program and then jump to the location that we've injected it, we will cause the program to run our own custom instructions. Recall Assignment 6 built around the grader program that fails to detect this write out of bounds and is thus susceptible to a buffer overrun attack. In the B attack, we didn't care what we put in the buffer array after our name. We just wanted to complete the stack smash to get down to getName stack frame and corrupt its stored return address so that we could return to a different location in main from where it was called. In the A attack, though, while we're still going to write off of the end of buff and get into getName stack, we're going to do a more complicated attack. Notice that after we get to EOF and read a new line character, readString copies the values that were read into the local buff into the name buffer in the BSS section. That means that, as suggested on that last much worse possibility slide, if we write instructions into the buff array, they'll get copied into the BSS section for us. And then, once they're there, instead of overwriting getName's return value with someplace in main, we can have it branch to the name array in the BSS section where those instructions have been injected and start executing them there. Let's take a look at how that would work. Let's look closely at the stack and BSS sections for the A attack. Again, I won't provide the full details with memory addresses or what goes where on the stack because you'll be determining those as you fill in your memory map. But this should give you the idea of the principles of operation of the A attack. Initially, when we enter into readString, here are the contents of memory. The buff array in readString is a local variable. It wasn't given an initialization, so the contents are just whatever bits happen to be in memory there already. In the global name array, though, all the bits are 0 since it's in BSS. First off, you will need to enter your name into the program so that eventually, way back in main at the very last print, it will thank you by name like it's supposed to. If we weren't trying to attack the program, you'd then just hit enter at the end of this line or close the input stream so that the program's call to fgetC would return EOF, and then the function would fill in the null byte after your name for you. But we don't want to end the loop, so we can't do that. But if we don't put a null byte, then the very last print will print beyond the end of our name. So after our name, we have to actually also enter a null byte to terminate the name string, even though we are not terminating the loop. Now, with that mundane portion of our input complete, we can inject our attack code instructions into the program by entering them after our name so that they get copied over into the BSS section after everything is read in. But what attack instructions are those? Our principle of attack for getting an A is going to be as follows. Store the character A into the memory location that holds the grade variable. This will require 3 pieces: getting the character A into a register, getting the address of the grade variable, and then doing the store from that register where we've put the A into the memory location referenced by the register where we've put the address. Then the last step will be to branch back into main to just after the call to getName. We can't just return there because we can't use the read instruction because the x30 value that getName would have had, we overwrote in order to get to these instructions in the BSS section in the first place. So we're going to have to do a branch to get back into main. But now with our name written and null terminated, and with a solid plan of what our attack code instructions are going to be, we can inject those instructions. For example, here we have the ARM instruction to find the address of the grade variable in the program's data section of memory. We need to put that instruction into buff after our name and the trailing null byte. But we can't just write an A and then a D and then an R and then a space. For one thing, there won't be nearly enough room in the BSS array for all the instructions we need. But more importantly, these are ASCII characters that are a representation of the instruction in assembly language. That's not how executable code is represented in a program. So to pull off this attack, we need to know what the machine language instruction corresponding to each of these assembly instructions looks like, bit by bit. And that will be the focus of the second half of this lecture. But before we get there, let's just finish off the operation of the A attack. So we write the rest of the instructions to change the grade in buff in readString stack frame. Now we redo the steps from the B attack. We fill out the rest of the buff array with arbitrary data until we write off the end of buff, and then eventually out of readString stack frame entirely. And then eventually overwrite the stored x30 value in getName stack frame. where we will overwrite it not only with an address in the text section, but instead with the address where the first of our injected instructions will be stored. They're not there yet, but they will be copied over into the BSS section, and we know where they'll be, so we can know that address a priori. So finally, the read string fgetC returns EOF. We've filled the buff with our name, a null byte, the attack instructions, and enough padding to write into getName stack frame, where we have written the address in the ADR instruction will be copied. So now we just have to actually do that, get the data from the stack to the BSS. And that's actually taken care of for us by the second loop, which copies exactly 48 bytes from buff to name. At this point, read string returns to where it got called from, getName. And the call to read string is the last thing in getName, so it's done too. GetName restores x30 from its stack and returns. But because of what we've done, instead of returning back to main, the program counter gets set to the name array in the BSS section, where we begin to execute our injected code and earn our A. You'll cover this attack in more detail in your final precept. So now let's turn to the details of ARM machine code. We know what the assembly instructions look like. We can now read them in English just at a glance. Add x1, x2, x3 is add the contents of 64-bit registers x2 and x3 and store the result in x1. And here's what the corresponding machine language instruction looks like. But it's not at all apparent, not at all human readable. It must, we know, contain the encoding of the verb and each of the nouns, if you will. But even with intense inspection, without substantial documentation, we can't make much of this. We could try to guess, like, hey, I see a 1 at the very, very end. Maybe that's corresponding to x1. As it ends up, it is, but it was nothing but a lucky guess. So we'll need to learn the overall structure of machine language instructions, and then additionally the specifics of each individual one that we're concerned with. Let's start off with the former. What pieces are part of a machine language instruction? Well, let's think back to our old friend toy. All instructions were the same size, 4 hexets or 16 bits. But we did have multiple different formats for instructions. Each one had an opcode which indicated the operation was. This is the verb, if you will. But some had 2 source registers and 1 destination register. These were the nouns. Others had a different set of nouns, an address or an immediate value to go with the destination register. So we have multiple different formats. ARM is going to look similar in some respects. All instructions are 32 bits long. This is an advantage of the RISC architecture. But there are a variety of different instruction formats. All of the instructions are stored in places in memory that have an address of a multiple of 4. That's a requirement of the hardware. This is to promote hardware simplicity, but also for reasons we'll see later that involve trying to get as much data into each instruction as we can. And each will have an opcode, and then bits identifying the registers, the memory offsets, the immediate values, etc. So it's actually a very similar principle to what we've seen in toy. So the rest of this lecture is going to fly through a bunch of examples of these, but you'll definitely want to look back at these slides as a detailed reference when completing assignment 6. Alright, so since all ARM instructions are 32 bits, we can be consistent about identifying them. We'll start out with the least significant bit and index from 0. So on the right here is bit 0, while the most significant bit on the left is bit 31. Of course, even though we've ordered the bits from most to least significant here on the slide, the byte order in memory is still little endian. Before we start our breakdown of the instruction, though, we need at least one more vocabulary term. Operation group. This is a grouping of opcodes that shares a common bond. For instance, branch instructions or 3-register data processing instructions. The operation group is encoded in bits 25 through 28, the red ones on the slide. But as you can see, as indicated by the X's for each group in the list, every operation group identifier doesn't necessarily use each of these bits. When those bits are not used for the identifier of the op group, they are typically repurposed, often for the detailed opcode. We'll take each of these operation groups in turn, seeing one or more examples of each that might be relevant to you in assignment 6. So our first op group will be the data processing instructions with 3 registers. We'll need the verb, the opcode. That's put as an extension beyond the operation group, 1 to the right in bit 24, and additionally over there on the left in bit 30. We'll also need 3 nouns, the first source register, represented here in green, the second source register, which is in orange, and the destination register, the blue bits. Note that each of these registers is allocated 5 bits as the identifier. This is the perfect amount to uniquely identify 32 registers. Count 0 through 31. Conveniently, we have 31 registers, count 0 through 30, encoded as their own number in binary. We also sometimes use either the 0 register XZR or the stack pointer register SP in our instructions, and so when we do that, those get encoded as 31. We also need to specify whether these registers are W or X registers, so that's the most significant bit, bit 31 here. And we can also specify whether the instruction should modify P states N, Z, C, and V condition flags. That's bit 29. So let's look at a concrete example, the add instruction from the motivation slide 3 slides ago. So our verb now is explicitly add, not just an operation doing data processing on 2 registers, putting the result in a third. No, we're doing add. That means that we're able to fill in bits 24, 28, and 30, as well as the operation group. So these are the burgundy bits. They are the operation group extended to the opcode. And our nouns are now explicit too. The green bits, 00010, we see that's the number 2 in binary, so that represents register 2 as the first source. The orange bits, 00011, that's 3, so register 3 is the second source. And the blue bits, 4 zeros and a 1, that's 1, so register 1 is the destination. The pink bit at the far left is a 1, indicating these are X2, X3, and X1, not W2, W3, and W1. And this is add, not add S, so the cyan bit 29 is 0. That's all the info we need. All the remaining bits here are 0. So take some time, pause the slide if you will, and see how we can break the 32 bits down into separate fields, each filled in to encode a piece of information that we already know about the assembly instruction. If this example is overwhelming, look back again over it until you do. You can go back to the previous slide with the overall opcode and operation group, and then come back to this one for the concrete example. Examples that come after all build on this same sort of structure and format, so it would be foolhardy to rush into them without a really solid grounding where you can understand what's on these slides. Okay, so our second op group will be data processing that has a destination register and then either a source register and an immediate or just an immediate. The 2 varieties will have slightly different formats to fit these variants. So our opcode in burgundy again spreads out beyond the core op group bits. The most significant bit in pink over on the left indicates whether we're dealing with W's or X's. Same thing as before. In one of these, the cyan bit 29 is there to distinguish whether to set condition flags or not, but it doesn't actually exist. There's no S variant in the other one. The destination is still the 5 least significant bits. This is a recurring theme. Most operations will try to share a similar structure, which simplifies the hardware that has to interpret these instructions. But now, whereas 5 bits were enough to indicate all of our registers of note, we need a lot more bits to indicate an immediate value of any reasonable size. Here we'll use 12 to 16 bits for the immediate value, which is a much more considerable range, though still not that big. 2 to the 10 is 1024, so 2 to the 12 is 4096, and 2 to the 16 is only 64K. So again, let's see a concrete example, this time one for each of the 2 variants. Our verb is now explicitly sub-S, not just an operation that does data processing on a register and an immediate. That means we're able to fill in bits 24 and 28 and 30, as well as the operation group. So those are the burgundy bits. And our nouns, again, are now explicit. This is the first variant. We have a source register, so we look at the green bits. 00010, we see that's the number 2 in binary, representing R2 as the first source. The orange bits, interpreted in binary, represent a 1 in the places 2, 8, and 32, so that's 42 in decimal. The blue bits, all zeros and then a 1, that's 1, so register 1 is the destination. The pink bit on the far left indicates that register 2 and register 1 here are W2 and W1, not their longer X versions. And this is subs, not just sub S, so the cyan bit is 20. The cyan bit 29 is 1. So again, now we've reached all of the information that we need. This is sub S. It's on W registers. It has a register 1 as the destination. It comes from register 2 with an immediate value of 42. Here's the second variant of data processing with an immediate, this time only with an immediate source and a destination register. Here we have a few more bits dedicated to the opcode. Even with the reduced instruction set, there's still quite a few different operations that we have to be able to specify. But beyond the verb, we actually only have 2 nouns now, the immediate value and the register. So let's take a look at the immediate first, since that's what's expanded. The orange bits, interpreted in binary, have a lot more leading zeros, so they could represent a much bigger immediate if we wanted them to. But in this case, we still only have bits for the 2's place, the 8's place, and the 32's place turned on, so those are still the offset 42, the immediate value 42. The blue bits are still register 1 as the destination. And we still need to specify whether it's W or X as a register, so now we've decided that this is a bit that has a 1 bit, so it's X. So next we'll move on to some more complicated cases that aren't as easy to interpret. But again, if these are still confusing to you, go ahead, pause the slide, see if you can draw it out yourself, take it a bit at a time, and see, is this one of the bits we care about? If it is, what does it mean? So thus far, our constant values, the immediate operands, have been absolute values. We saw 42, that meant 42. But consider that some literal values might be too big. For instance, how could we possibly put an entire arbitrary 64-bit address into a 32-bit instruction? We can't. Thus, we have to work around this constraint. Some instructions will use relative values instead. 2 different instructions in the text section are likely to be in a relatively small number of bytes apart from each other, certainly not far enough apart to need 64 bits to address the difference. So addresses and numbers that are well aligned, recall well aligned here means some multiple of a specified power of 2, often 4 or 16. Numbers that are well aligned require fewer bits to store if we know about this property. To see why, consider in decimal that if I ask you to represent the number 2,500 as the number of hundreds, you can do this with just 25, just 2 digits, as opposed to the 4 of the full 2,500, because you know the trailing 2 digits are zeros. So our next group is branches, which will have an opcode, a relative address, which we know must be 32 bits long and 4-byte aligned, based on what we claimed about instructions. If every instruction is 32 bits long and 4 bytes aligned, branches reference instructions, so it must reference something with those properties. And potentially a branch has a condition code. We won't store the entire address because we can't. We can't store an entire 64-bit address in a 32-bit instruction. So we'll store a relative address, which should be smaller. And we won't store the last 2 bits of that relative address because when we subtract 2 numbers that are both multiples of 4, we know the result will be a multiple of 4. So let's take a look at a few examples. First, the unconditional branch. The only 2 pieces of this instruction are the opcode, in burgundy as usual, and the relative address bits in orange. In this case, the orange looks gigantic. But we interpret this as 2's complement. We can branch forward or backward, so our relative address can be either positive or negative. So we flip all the bits and add 1. This turns the 24 leading 1s into zeros and a trailing 1, 1. This looks like -3, but it's not. This is the result of right shifting the value by 2. So that means we have to left shift it to restore those 2 trailing zeros. We end up with 1100, which is 12. But we did do the 2's complement to get this value because it was negative, so our relative address here is -12. We're jumping backwards in the program. And since each instruction is 4 bytes, -12 as an offset means jumping back 3 instructions. The BL instruction, remember this is to make a function call, is very similar to the unconditional branch. It actually is unconditional. It's just that there has to be a little bit of extra encoding to specify the detail that it has to put x30 as the value immediately after the call. So that is, it has to fill in the return address for the function that it is calling. And this means that it needs a different opcode, 100101 versus 000101. And this is really just there to say, okay, in one of these variants I have to do something with x30 and then unconditionally jump. In the other one I don't have to do anything, I just unconditionally jump. So other than that, though, it works identically. And all of the rest of the bits, other than the opcode, are just the relative address right-shifted 2 places. The last example of a branch instruction is a conditional branch. Here, recall that we have fewer bits for the relative address because we have to use some of the bits for that condition code. In this case, we have 4 bits, so there are 16 conditions that we can represent in branches. Though not all of them are actually used, there's a BNV instruction, which is a mnemonic for branch never. But here we have 1101, which is for LE. And the full table of all of the mappings from the 4-bit code to the assembly language mnemonics will be in a precept handout. It's taken from C124 of the ARM Architecture Reference Manual, but you can just reference the precept handout for the A attack and very likely your A+ attack. So in this instruction, we have 19 bits for the relative address, which works identically to how we've seen it before. Note in this example, we're branching 3 instructions later rather than 3 instructions earlier, just for demonstration and variety. So we didn't have to do the 2's complement conversion. We can just take the number at face value, but we do still have to left shift it by 2 bits because the addresses were multiples of 4, and we shaved off those trailing 2 zeros to make better use of the limited bits that we have in the instruction. So the penultimate operation group that we'll consider are memory operations, loading and storing. Here, even though we're dealing with memory, recall that our operations use registers and dereference them, so we don't have to store actual memory addresses in the instruction. We do, though, have to consider more complicated memory addressing modes. We'll see 2 here, register immediate offsets and register offsets, where the value of the offset is stored in some other register. And we'll see in passing a mention that the black bits of additional information are where we would store the scaled register offset mode if we were using that. Furthermore, we also have a more complicated source and destination metadata than just X or W. These instructions have to differentiate between loading and storing a byte, a short, an int, or a long. So let's look at 3 variants. One with a register offset, one with an immediate offset, and one that stores only a single byte. That last one should perk your ears up a little bit as you try to think about writing the character A into the spot in memory where the character D initially resides in the A attack. So I hope at this point you've become a pro at deciphering these slides, at least so long as I keep color coding them. But let's run through this one again in moderate detail. We now have 2 pink bits as the most significant bits on the left, instead of just 1. Both are 1 here, so we're dealing with X registers. We have the opcode for load using the register offset addressing mode. And then we have the first source register in green is an actual source register, so here X1. And the second source register in orange is the offset register, here X2. And then the destination register, as is typically the case, is the least significant 5 bits, marked in blue, here indicating X0. For the immediate offset, let's do a store for variety because there's not a whole lot of difference at first glance. The two pink bits indicate the size, which is either a byte, a short, an int, or a long. Again, the opcode is in burgundy, and though ARM does choose to use a slightly shorter opcode here, it gets an extra bit for the offset versus before. Offsets could be larger, whereas the register is always just going to be a 5-bit register name. So we want to maximize the possible size of the offset. For hardware consistency, we're still going to use the least significant bit for the first operand in blue, But because this is a store, the semantics are flipped from most instructions. And so this isn't actually the destination, it is in fact the source. The green bits represent the second operand. Typically we've thought of this as the source register, but likewise, because this is a store, these are actually the destination. Here ARM uses 31 to represent SP, since XZR0 isn't a useful memory location to offset from, and we will instead often offset from the stack pointer. And that leaves the rest of the bits as the offset value. Note here that because the pink bits were 1, 1, we're dealing with longs. So we know the address should be a multiple of 8 for good architectural alignment, and thus we can assume the address will have 3 trailing zeros. Thus we can save some bits by shaving off the 3 last bits in the offset, right shifting by 3. But if it's stored right shifted by 3, to interpret it we have to do the opposite and left shift by 3 to restore the 3 trailing zeros. So when we see this 1, 1 value, that's really 1, 1, 0, 0, 0, which is 24. Now let's compare the STR we just saw with STRB. The bit allocations, the colors if you will, are identical. The opcode is identical too. It's still register plus offset. The register values, in fact, are also the same, storing from register 0 and storing into an offset from SP, register encoding 31. What has changed, though, is the 2 pink bits. They're now 0, 0, meaning a single byte. We saw this 3 slides back introducing the operator group. 0, 0 is a single byte, 0, 1 is a short, 1, 0 is an int, and 1, 1 is a long. Since this is a single byte, we don't necessarily have 8-byte alignment, and thus the offset is not right-shifted in the instruction. So interpret it, we don't shift back to the left. We interpret it as it is to get 24. This means we have relatively less range of offsets by 1 than we did by 8. The last instruction that we'll talk about is ADR. It has the bits 100x, like the operation group for data processing with an immediate and a register, but it's a special case. It's distinct from that other op group. For an ADR, we might be referencing something farther away in memory. Unlike with a branch where we're just jumping within the text section, except in your A and A plus attack. So we might have a label in text or RO data or BSS, and we'd like to be able to maximize our range of our relative address. So to get 21 bits for the relative address, but maintain where the destination and the opcode go, we have to split up the bits. The 2 lower order bits are in bits 29 and 30, the mint bits here. The 19 higher order bits of the relative address are in 23 through 5 in orange. This means we're going to have to do some bit whacking in order to interpret these instructions. Let's take a look. Let's try a small offset so that the numbers are easy, but we'll still show what we need to do. Here you're familiar with the destination register as the least significant bits, and we see the opcode. So that leaves us with only the tricky split offset. The orange bits, the 19 high order bits, the mint bits are the 2 low order bits, so we can just concatenate the mint ones onto the end of the orange ones. Of course, the actual bitwise operations to accomplish this would be more involved, but on the slide, I can concatenate it. It's nice and easy. When we concat 1, 0 onto the end of 1, 1, 0, 0, we get 1, 1, 0, 0, 1, 0. That's 32 plus 16 plus 2. We have a relative address of 50 bytes. So now that you've seen a few instructions that are ready to run, we'll be ready to go even slightly lower next time and see how instructions actually get constructed by the assembler and then fixed up by the linker. In this lecture, we've seen a bunch of relative addresses and offsets, what happens when those addresses aren't known at assemble time. For instance, they're an external library that hasn't been linked yet, or maybe they're in a different section of memory that we don't know the address of yet. That's all next time, to finish up the concept baked into your mini-assembler implementation for A and A+ attacks. And indeed, next time not only finishes off the details for Assignment 6, but it also finishes up the course material as a whole. So I look forward to getting one more opportunity to grace your screen. Until then, though, keep working hard on Assignment 5, and good luck.